Here we go. So let's talk about science autonomy. First off, what we're doing these days with rover exploration is not science autonomy at all, right? Nowadays, we have a very tight command and execution cycle where a team of operators and scientists command a rover on a piecemeal basis. Every single movement and every single measurement that the rover performs has been commanded. If the planet or asteroid happens to be far away, this process can be extremely slow, as we have seen with Mars exploration. In addition to that, data volumes and data rates can be pretty low, so you can never get a full assessment of a site because you just can't return all the data that you would need to get a full assessment. So basically, most activities are decided based on limited knowledge of the site. So in this new paradigm, what we propose is that the rover activities are not dictated by ground control. It's that the rover basically all of the activities and measurements are open-ended and responded to the measurements that the rover is making. In this paradigm, the rover actually participates in data analysis, data processing, decision-making, route planning, and so on. So the process starts basically with the scientist, providing the robot with a set of the driving hypotheses of the mission. In other words, the actual scientific hypothesis encoded in a way that the rover can understand. The rover uses this and information about the site to plan a traverse and a measurement plan. And as it performs this plan, it acquires data and analyzes the data, addresses the hypotheses with the data, weighs the hypotheses, basically, as some hypotheses become weighted towards greater likelihood, whereas others become weighted towards less likelihood. And at the end of this cycle, basically, this cycle could be a day, a week, or when the rover finds something that was unexpected and not included in the hypotheses, it stops and contacts ground control and sends the data back to the scientists along with the updates on the hypotheses, the updated hypotheses that it has basically updated based on the data it's acquired. So, of course, the advantages to this method I would expect is improved operational efficiency because there's no humans in the loop, at least not at every point of the activities, and an improved science return, because if you don't have to return all the data, you can acquire gobs of data, analyze it, make decisions based on that data, and then you can send back the parts of the data that are actually relevant. So at the core of this paradigm is the hypothesis map, which represents the basis for decision-making and reporting by the rover. It's very general, and it can be applied to pretty much any situation. In our case, we were interested in having the rover constrain the geologic origin of the site. So our hypothesis map corresponds to basically multiple layers of these different potential geologic origins. And as the rover drives around, basically, it updates the hypothesis map based on the observations it collects. And eventually, this updated hypothesis map is what is sent back to the scientists. Sorry, that went too fast. In order to collect information, process the information that it collects with the instruments, the rover needs to have some data analysis capabilities. In our case, we were using a spectrometer, so you use tetracorder, which is a system capable of automated spectral analysis. It looks at multiple portions of the spectrum concurrently, so you can identify multiple minerals from the same spectrum. This module was running in real time on the rover as it was driving around. And the third thing is science interpretation algorithm. Basically, how do you go from mineralogy to the actual hypotheses of geologic origin? So we created a basically set of nested lookup tables, which take you from basically basic mineralogy to geologic origin. In some cases, mineralogy depicts very evident unique geologic origin, but in other cases, mineralogy can relate to multiple possible geologic origins. So you can see that there's greater uncertainty here than here in the geologic origin assessment, and that's important. So here's how we built this hypothesis map. Like I said, it's actually a hypothesis cube. Each one of the layers is a map of the site, and basically each plane represents a different hypothesis. The pixel value at any one plane corresponds to the likelihood of that hypothesis at that location. So the more minerals that are detected associated to that hypothesis at a location increases its likelihood. And on the flip side, the more planes containing a non-zero value at that specific location, the greater the uncertainty for the pixel. So now you have a probability cube and an uncertainty map. So the rover's job is to disambiguate the geologic origin of its terrain. And the best way to do it, we do the same thing. We go to places of the greatest uncertainty to be able to get up to ascertain and basically constrain that uncertainty, right? So in building the hypothesis map, basically we use average hyperspectral data, which has a similar spatial resolution as a CRISM on MRO or M-cubed on LRO, so it's consistent. And then we had a science team, which was remote, and who basically analyzed the data and built the map. And it consisted of three things that we provide the rover. This is the geologic origin cube, the uncertainty map, which we discussed, and then a photogeologic map. Because as the rover drives around, it does this little noodle on the surface, but other places on the map that are related to the places the rover is exploring would also be updated based on what the rover is finding at that place. In this case, geologic units. So here's an example of data analysis. Basically, we start with the average. Here's an RGB of it. And basically, we produce maps of every mineral in the USG spectral library. These are converted then to these feed into the geologic origin cube. And here's 4 planes of that cube. And you can see variations in likelihood for each one of those. And then having this information, the rover can start planning out a traverse. The scientists can also provide some requests as to where to go explore, and the rover can fold in those requests into its traverse plans. And as the rover drives around, it basically updates the map in real time. Okay, our field campaign involved the Zoe rover from Carnegie Mellon, and to perform the automated portion of this, we used two instruments: the spectrometer, which is mass-mounted near-infrared spectrometer, and then a Fourier transfer infrared spectrometer, which was handheld, and it was as if it was simulating basically having an extendable boom, kind of like putting the instrument down on the surface. So the site was Yellow Cat, which is just north of Arches National Park. It was not a very big site in this case. It's only about a couple kilometers across on each side, and it's very traversable. So it was all the issues of rover automation for traversability and so on were not the thing we were considering here. So we wanted something that would be simpler to traverse. But it was very colorful and rich in spectral variability, so that was a great attractor. We know the geology of the site quite well, so that's also an additional advantage. Now, the science team that was placed in a room elsewhere for these simulations did not know where we were, so they had to figure out everything about the geology base from their room. So we basically tried 3 different scenarios. One which was human-directed exploration, rover-directed exploration, and then we also tried a collaborative exploration between astronauts and rovers. This last one I'm not going to talk about, but look out for papers by Maria Banks. She'll be talking about that a lot. Sorry?
1 minute.
Oh boy. Okay, so we compare science yield and operational efficiency. There's your geologic units. Here are the original hypotheses. Basically, you can see there's a lot of competition between the different hypotheses for each unit. And that's the rover traverse. Each one of those markers marks an observation. The red markers mark science stops. We also did FTIR. And this is how the hypotheses evolve for each unit. Here's 3 examples for 3 units, and you see how the hypotheses become weighted really fast as some just drop to 0. In some cases, a few don't drop to 0, and we found out that has to do with the fact that we have multiple competing geological processes. You might have fluvial equestrian deposition followed by diagenetic processes, and that is reflected actually in the hypothesis map returned by the rover. So starting and ending, basically, it converges really well. And they were actually correct based on the geologic assessment. And here's the metrics, basically, the first scenario shown here, and the 2 scenarios with the rover, different ones were shown here. In all cases, the rover-directed scenarios basically acquired a lot more data per hour, analyzed more data per hour, covered more terrain per hour. So overall, it was more efficient and collected more science data. So scientifically, a greater science yield.
We are at 10 minutes.
We'll just leave it at that and answer any questions you guys have any.